Thank you for joining us for seminars today. Today here we have Dr. Bill Wannop with us, who is presenting on footwear and sport surface research. Dr. Bill Wannop is an assistant professor of biomechanics here at the University of Calgary and also the editor-in-chief of Footwear Science. So if your papers are rejected, it's probably not. Only mine, he said. He did his Bachelor of Kinesiology in Biomechanics here at the University of Calgary, and then went on to do a PhD in Kinesiology as well at the University of Calgary. After that, he also did a postdoc fellowship under the supervision of Dr. Darren's definition, and then went on to be an assistant professor of biomechanics. When asked what is an interesting fact about him, he says he loves Mexico and the beach, and so he goes there any chance he gets. But now that we're not here in Mexico, he will be presenting on his talk today.
Thank you very much. So for those unaware, I know I've been here a while, but I just started as an assistant professor. My main area of research is in sport biomechanics. And really the goal of my research is to either improve athletic performance, as shown here during some sprint studies we've done, or to reduce athlete injury risk, as shown down here. So the video is a little blurry, but the goal is to try to prevent athletes from becoming. And the main way we do this is through two main interventions. The first being footwear. So altering different components of the shoe, the cushioning, all sorts of components, or sports surfaces, particularly infilled artificial turf, as well. We're starting to work on some hard-court basketball surfaces. So I'm going to go through both of these interventions, and the first thing I'm going to start with is footwear. So footwear is the main piece of athletic equipment in many sports, and various studies have shown and researched a lot of properties of footwear that can be altered. So properties such as the forefoot bending stiffness, as shown here during two tests where we're quantifying the resistance to bending about that MTP joint. Mass can alter both injury and performance, cushioning, as well as the geometry or curvature of the shoe that can have effects on both performance of athletes as well as injury. The last component is what I focus the majority of my research on, and that is outsole traction. So traction is a property of both the shoe and the surface, and in general, researchers will break traction down into two components. The first one being translational traction, which is thought to be very important for performance, and that's simply the resistance to the shoe sliding on the surface. And the other component is rotational traction. So that's the resistance to the shoe rotating on the surface. And it's generally been speculated that rotational traction is associated with injury. So going back over the history of traction, footwear traction and injury research, we go all the way back to 1971, a study by Torg et al. And this was an observational study. And what they did is they simply looked at the shoes athletes were wearing, and they found that when athletes wore this soccer style shoe that's highlighted in red, so it had a larger number of smaller cleats, that they had a decreased severity of injury in this shoe compared to the conventional football shoe worn at the time. So this had these longer studs. And he attributed this decrease in severity of injury to a decrease in the traction of the shoe. This was another study a couple years later by Cameron and Davis, was termed the swivel shoe study. So they kind of took the results here of that association of traction and injury and went a step further and actually developed a shoe. So this is a swivel shoe. So they put a movable turntable on the forefoot of the shoe. And this turntable was locked until a specific torque or force was reached, at which point it was able to release and rotate. And the goal again was to reduce the rotational traction. And again, another observational study, they found that when athletes wore this swivel shoe compared to the conventional shoe that was available at the time, that there was a lower percentage of athletes that were injured in the shoe, again attributing this reduction to a decrease in the rotational traction. And lastly, we go to a landmark study by Lamson et al. In 1996. So what he did again in American football is he grouped athletes' cleats into 4 categories. So there was cleats that he termed flat cleats. So these cleats were all the exact same size on the outsole. Screw-in cleats, so these are the removable cleats. A pivot disc, which was very similar to the swivel shoe cleat. And then these edge cleats. So these edge cleats that are highlighted, they have a larger cleat around the, or larger length of cleat around the perimeter of the outsole. And he found that athletes that wore that edge cleat design had a significant injury in ACL injury. And again, this was attributed to the higher rotational traction of those edge cleats. So all these studies showed this link between traction and injury, but it was mostly some indirect evidence of this association. So for the first study of my PhD in 2012, I wanted to look and try to examine and see if there's a direct link between this traction of the shoes and injury of athletes. So I conducted a 3-year study that involved 555 male high school football players. And what's unique about Calgary is that all high school football games are played at Shouldice Athletic Park. So that's the athletic field down by the river along 16th, right down Home Road. So all athletes are going to play on the exact same surface. So what we did is that we collected and we wanted to measure the athletes' actual footwear they are wearing on the actual field of play to get their traction. So what we would do is we would go to their practice after we'd go to their school after their practices, we'd collect all the athletes' shoes, we'd then bring the shoes to Shouldice, and we'd record the translational and rotational traction of those shoes on the surface that they're gonna play their games. And we use this portable traction testing device. So this device was allowed to, so we could provide slide tests or a translational traction. As well, we could rotate the shoe to quantify the rotational traction. We then had athletic therapists follow these athletes over the course of their season, and they reported lower extremity injury data such as the mechanism, the severity, as well as the surface that these injuries occurred on. So for the study, we had both the traction of the athlete's actual footwear, as well as any injuries that the athlete suffered throughout the season. And the main result we found here is injuries per 1,000 game exposures. And what we did is we grouped the athlete's shoes into 3 bins or categories. So whether the athletes had low traction, a medium amount of traction, or high traction, and this is rotational traction. So there's an equal number of athletes in each of these bins. And what we found is that athletes that had shoes that had low traction had a significant reduction in injury compared to those that had medium as well as high traction. So this study showed with some direct evidence that high rotational traction seems to be associated with an increase in injury risk. So we found that high traction is linked to injury. However, we're still not really clear on what the mechanism of that injury is. So why does simply having high traction of shoes lead to these non-contact injuries? And it's been speculated that this may be due to biomechanical joint loading. Specifically, knee and ankle resultant joint loads are the resultant joint moments. So it's been shown that these non-sagittal plane ankle and knee joint moments have been associated with lower extremity injury. So it's thought that increasing rotational traction leads to an increase in these joint moments and joint loads. So the purpose of the second study that we did in 2016 was to try and examine and determine whether this is true. So we developed a control shoe. This was simply a flat-soled shoe that we installed and put these removable cleats, so these screw-in cleats in the forefoot in the orientation shown here. We then mechanically measured the translational traction and the rotational traction of the shoe. We then created another shoe model that we termed low rotation. So for this shoe model, we wanted to reduce the rotational traction. And the way we did that was by moving these cleats. They're the exact same shape and size of cleats. We just moved them closer to this center cleat. So the center cleat somewhat acts as the center of rotation. So by moving them closer to that center rotation, we're gonna decrease the rotational resistance of that shoe. And by using the same shape and size, we didn't actually influence the translational traction. So altering the cleat pattern, the translational traction was exactly the same as the control, but we did reduce that rotational traction. We then wanted to also look at the influence of translational traction. So in this case, we kept the orientation or the location of these cleats the same, but we added these small plastic fins to the base of them, so we made them slightly wider. And when we mechanically tested these shoes, we saw a significant increase in the translational traction, but no change in the rotational traction. So with this study in these shoe conditions, we could see the individual effect of altering the rotational traction by comparing low rotation to control, and the individual effect of increasing the translational traction by comparing the control to the high translation. We then had 10 male athletes perform a variety of cutting movements in these 3 different cleat conditions. We used our motion capture system downstairs. So we used the cameras and the force plate. And using an inverse dynamics analysis, we calculated and quantified the lower extremity joint loading. So the resultant ankle joint moments and the resultant knee joint moments in each of the conditions. So here's the results. On the top left, we have the peak ankle transverse plane moment and the peak knee transverse plane moment. And in the center, we have the peak knee frontal plane moment. So just comparing the control to the high translation shoe, so the shoe that had high translational traction, there was no significant differences between any of those peak resultant joint moments. However, when we compare the data to the low rotation shoe in red, so the shoe that we decreased the rotational traction, we had a significant reduction in both these ankle and knee joint loads, so these joint moments. What we concluded from this study was that high rotational traction was associated with increased joint loading represented by these joint moments. So going over the results that we attained so far, so high rotational traction was linked to an increase in athlete injury risk. High rotational traction was also linked to an increased lower extremity joint load. So if we can compile all the data that we learned so far, we can create this traction spectrum. So going from low to high traction. And from our previous work, we kind of showed that high traction results in lower extremity, an increase in lower extremity injury risk due to these increased joint loads. So the question becomes, why don't we just make traction as low as possible? Because we would then make these athletes kind of as safe as possible. So one of the issues with that is if we make the traction too low, the athletes could actually be injured due to a slipping incident. So if traction is not sufficient, they could slip, fall, and potentially become injured. And a prime example of this was last year's Super Bowl. So this game was played on a natural grass field, but it was a field that had very low traction. And we can see from these videos, the athletes were actually slipping all over the place and putting themselves in orientations that were likely going to be a very high risk for them. So if we don't have enough traction, we also increase that injury risk. So what this allows us to do is create a theoretical injury traction curve. So at very low tractions, we have a high risk of injury because the athletes don't have enough traction. They're going to slip, they're going to fall, they could become injured. As we increase this traction, we decrease the injury risk. But as we further increase the traction, injury risk again starts to increase due to those increases in those lower extremity joint loads. However, there's another aspect that we need to consider when talking about traction, and that is performance. So if you talk to any player or coach, they're going to tell you that in regards to traction, that they want as much traction as possible because they want to maximize their performance. And a study by Gung Liu and Darren's definition in 2011 aimed to test that statement. So they wanted to see whether if you continually increase traction, do you continually increase athletic performance? So they performed testing on male athletes in 4 different shoe conditions, and these shoe conditions differed in their traction values. So they went from very low, low, high, and very high. And the way they did this is they had athletes running around in a circle as quickly as they could in each of these shoes. And the performance metric was the maximum speed these athletes could achieve in each of those conditions. And what they found, so here is a speed traction curve or speed traction result. So when going from very low in red to low, there was a significant increase in the athlete's running speed, so the athletes increased their performance. Again, going from the low traction to the high traction shoe, again, we see an increase in this running speed, the maximum running speed the athletes could achieve. So again, a significant increase in the athlete's performance. Going from high to very high though, when we compare that result, there was no significant effect on the athlete's maximum running speed. So the performance of these 2 athletes, even though we had a substantial increase in traction, was the same, so there was no change. The Darren and Gung concluded that there was a critical threshold in terms of traction and performance. So once you pass the threshold, you've achieved optimal performance. And no matter how much you increase the traction of your shoe, you're not going to further increase your performance. You've reached that threshold. So this allows us to now plot on this same traction spectrum a performance traction curve in blue. So at very low traction, we have a reduced performance. They don't have enough traction to perform maximally. But as we increase traction, we get an increase in the athlete's performance until they reach that critical threshold. Going above that critical traction threshold, no matter how much you increase the traction, the athlete's performance is going to stay the same. And what you actually do by further increasing that traction, you just increase the athlete's injury risk. So by using all this previous data that we've collected, this allows us to kind of identify a target design space in terms of outsole traction. So this is the region of this traction curve where we want to aim to design our footwear, our sports surfaces. So within the region where athletes are attaining maximal performance, but we're still trying to keep the traction low enough that we're not going to unnecessarily increase the athlete's risk of suffering an injury. So the goal of traction research that we perform is to optimize traction to have maximal performance while ensuring and trying to keep athlete injury risk as low as possible. And I'm just going to go through an example of how we used all this past knowledge to work towards some footwear innovation and some footwear designs. So this was a study we did for World Rugby in 2018. So rugby is a very popular sport worldwide. And in fact, rugby has a large percentage of non-contact lower extremity injury risks. However, if we compare rugby boot design over the past couple decades, there's really been not a lot of change. So here's a sample shoe that was used in 1954 compared to a rugby boot in 2018 when we conducted this study. Well, there is some changes in the materials, but overall, the general concept of the shoe is relatively similar. So it's generally composed of 6 to 8 metal studs around the perimeter of the outsole. And it's not really been innovated and changed like other sports have. So the goal of this project was to see if we could come up with a more modern or different cleat design in which we could optimize the traction of the rugby boot. So the first thing that we needed to do to accomplish that is to determine the traction requirements of rugby players. So once we know how much traction these rugby players need to perform maximally, then we can work at designing and ensuring that we maintain that traction while potentially reducing it in regions that they don't need it. Once we've developed a new cleat design, the cleat design should have maintained translational traction to optimize performance, and this new cleat design should reduce rotational traction in order to reduce lower extremity injuries. So for the first phase of this study, we wanted to determine how much traction these rugby players actually needed during their movements. So we had 26 male rugby players, and they performed a variety of rugby movements in the lab downstairs. And they performed them all in this conventional rugby boot provided by Under Armour. So they performed sprinting, cutting, passing, and rucking, so a sled push movement in this boot. And our overall goal was to create what we termed traction maps. And so what these traction maps do is they determine the required traction magnitude, so how much traction they need. They determine the required traction direction, so what direction they need this traction in, and the required traction location, so where on the outsole do they need this traction. So here's a sample traction map of an athlete performing a V-cut movement. So we can see as this moves through, for every percent of the stance phase during their cutting movement, we get these little arrows. So these arrows, the color indicates the magnitude of the traction. The way the arrow is pointing indicates the direction of the traction. And the location of where they are on the outsole indicates where they're using or where they require that traction. And the way we get this is using a force plate, a in-shoe pressure sensor, as well as the motion capture system. So the force plate allows us to create the traction vectors to get the magnitude and direction. Traction is just the ratio of horizontal to vertical force. So we collect the horizontal and vertical force from our force plate, but when the athlete performs their movement, they actually have a foot orientation that is different than the force plate orientation. So when we get our forces, they're relative to the force plate coordinate system. So using the motion capture system, we have to put this force plate coordinate system in the coordinate system of the shoe. So we just create a rotation matrix, and now all our forces are relative to that shoe sole. We then put this insole pressure sensor into the shoe. So this is a sensor that is composed of around 99 small sensors. So each of these sensors will record the force and the pressure at each of these different areas. So each of these is its own individual sensor. And by setting a threshold and looking at this pressure data when they're performing their movement, we can determine what parts of the shoe are in contact with the ground during what time. So once these, each of these sensors passes our threshold, we can say that those aspects of the shoe are in contact with the ground. So that determines the location of where the required traction is. The force platform allows us to determine the traction magnitude and direction. The motion capture system allows us to determine the foot orientation, and the in-shoe pressure sensor allows us to determine the location on the outsole. And here's just two more examples of some overall resulting traction maps. So this is just during the braking phase of sprinting. So we can see the magnitudes, the directions, and the locations of the required traction during that braking phase. And as well, this is during the propulsive or the push-off phase of a sprint. So if we take that data for all the different movements, we can then create an overall traction map. So this determines the traction requirements in the different regions and different directions of the shoe. So this is what we use as our design metric. So from all the data, we determined that we would need a traction of 1.7 in the anterior direction in the toe, 1.5 in the medial direction and in the midfoot, 1.6 in the anterior lateral direction, the midfoot, and so on. So once we have that required traction of these athletes, we can then move towards developing our new cleat pattern. And we did this using 3D printed cleats and this carrier outsole that was provided by Under Armour. So by 3D printing the cleats, we had different shapes, different sizes, different orientations, and we could put them in a bunch of different locations on this outsole. So this is a very iterative process. So what we did is we created kind of a best initial first guess. We then mechanically tested both the rotational traction as well as the translational traction. And translational traction, we did it in these directions, which matched up with that traction map. And the goal again was to find a cleat pattern that reduced rotational traction while maintaining the translational traction in these slide directions. So a very iterative process. So at the end of that mechanical testing phase, we came up with a new cleat design. Oh, got these results. New cleat design. So again, this is the control shoe, and this is our prototype using those 3D printed cleats. So what we had is a significant reduction in rotational traction. So again, that's what we were aiming to do initially, try to get that rotational traction as low as possible. And then here is the translational traction results of that mechanical testing. So here we have control in black, prototype in red, and each of these numbers corresponds to the different slide direction. So what you'll notice, although the prototype shoe does decrease the translational traction compared to the control on certain directions, this white dashed line represents the required traction or the amount of traction that the rugby players were using in our previous phase. So as long as we had traction above this white dashed line, these athletes should have sufficient traction in order to attain maximal performance. And in each of these movements locations, they passed that white dashed line. The last phase of the study was the validation phase. So we wanted to see whether we were successful in designing a new cleat pattern in our prototype shoe that acted to reduce rotational traction and therefore reduce the joint loads of the athletes. So we had 15 male rugby players, and they performed again lab testing in the control and prototype shoe. And we had both in-lab and in-field testing. So for in-lab testing, we had them do the sprint, pass, cutting, and rucking movement again. We quantified the resultant joint loads at the resultant joint moments at the knee and the ankle joint. As well, we did some subjective assessments because we wanted the athlete's opinion on how this new cleat pattern felt in terms of their traction and their performance. We then performed some in-field testing, and the goal of this was to just ensure that they had adequate performance to perform maximally. So they just did a cutting drill as well as a maximum effort sprint. So first, in terms of the in-lab testing, so here we have the peak ankle moments on the left and the peak knee moments on the right in the transverse and frontal plane in the control shoe in black and the prototype shoe in red. And similar to what we saw previously, as we reduced that rotational traction, we got significant reductions in the transverse and frontal plane ankle joint moments. As well, we got a significant reduction in the peak knee frontal plane moment in that prototype shoe. So we were successful at reducing those joint moments and those joint loads. Next, here's the result of that performance testing that we performed outside. So for the agility drill time on the left, there was no significant difference between the two shoe conditions. And similarly for our sprint acceleration performance test, no significant difference between those two shoes. So even though we altered the cleat pattern, athletes still were able to attain their maximal performance. And this is probably the most interesting thing. So this is the subjective assessments, or this is quite interesting to us. So here we have the athlete's subjective assessments for traction during sprinting, cutting, rucking, and passing. And here's their subjective assessment of performance, the same movements going from very low to very high. The control shoe is in black and the prototype shoe is in red. So although it's not significant for all of these different metrics, we can see for the majority and in general, athletes felt that they had more traction in the prototype shoe, as well they felt they had slightly better performance in that prototype shoe. So they had no feeling that we removed traction elements in certain locations. So as a summary for this project, we developed a new cleat pattern for rugby. This new cleat pattern reduced the joint loads at the knee and ankle joint. Athletes were able to maintain their performance, and athletes actually subjectively preferred this new cleat pattern. So currently we're doing a follow-up study to this, again with World Rugby, and the goal is to look at the traction requirements of female rugby players. So this study had all males. So now what we want to do is see, do females require the same traction as males, or do females perhaps need a different traction pattern compared to male athletes? So in terms of our two focuses, I spent quite a bit of time on footwear. So now I'm gonna briefly touch on some sports surface research that we've done and we're gonna currently do. And this research is gonna be focused again on cleated footwear and on non-infill artificial turf. So in terms of artificial turf, it holds many advantages to natural grass. So mainly it's composed of a lot of different components, and we can alter these components, and altering these components will change the mechanical properties of the surface. So in a common artificial turf system, it's composed of a shock pad, so we can alter the material or the presence or absence of that shock pad. So some systems don't have a shock pad, while some systems do. We can alter the infill, so this is those black pellets that are in the artificial turf surface. So we can alter the material, the amount of them present, as well as the density or how tightly compact those infill pellets are. And we also have probably the most obvious one is the turf fibers. So we can alter the length, the density, the arrangement of these fibers on the surface. So we partnered with Field Turf, so they're a Canadian artificial turf manufacturer. They do turf for a bunch of different sports, and a lot of fields in the NFL are actually a field turf. So the study that we did with them was to go systematically through each of these components to see how they influence the traction as well as the athlete patterns or athlete biomechanics. So I'm just going to briefly highlight the main results that we saw with those studies. So first, we examined the shock pad. We had 17 male athletes performing on 5 surfaces, and they performed continuous running, they performed sprinting, as well as cutting movements on each of these surfaces. And these surfaces had systematic changes in the underlying stiffness by changing or removing that shock pad. And it's all relative to the control, which is just the common surface that field turf would install in a sports setting. And the main outcome of this project was to look at the athlete's performance. Did the stiffness of the surface alter their performance? So what we found, there was significant difference during continuous running. So both the softer and the soft surface improved performance compared to this control. There was no difference during sprinting, but during cutting, there was a significant increase in performance in the softest surface, again, compared to this control surface. So surface stiffness does appear to be able to alter athletic performance. The next aspect we wanted to look at was infill. So we've tested a bunch of infills over the years. So the control is simply the black rubber infill that's commonly used, but we tested a bunch of different synthetic materials as well as some organic materials. And first, just looking at how changing these infills alter the rotational traction. And we could see specific infills do significantly reduce that rotational traction. As well, by changing the infill, we can increase that rotational traction. So altering the infill can change the traction properties of these surfaces. As well, we did some biomechanical tests, and here's just one result. This is the peak ankle inversion angle. So when athletes performing a V cut or cutting movement, altering the infill material can significantly alter this peak ankle inversion angle. So the athlete's movement patterns are in fact changed, even though these changes in traction are not super substantial. So from this study, we can conclude that infill can alter the traction properties of the surface, and it can lead to altered athlete movement patterns. And the last component that we wanted to investigate was the fibers of the surface. So we had 13 surfaces that had systematic changes in 3 main components of the turf fibers. The first was the stitch rate. So that, comparing turf 1 to turf 3, is the distance between adjacent fibers. So this one has 9.5 stitches per 10 centimeters, while turf 3 has 14.4 stitches per 10 centimeters. There's more fibers in turf 3. The gauge, so that is the distance between adjacent rows of fibers. So comparing turf 3 to turf 4, turf 3 has a gauge or a distance between adjacent fibers of 9.5 millimeters, while turf 4 has a gauge of 19 millimeters. And lastly, we looked at the presence and absence of a thatch layer. So the thatch layer is just these smaller fibers that are right along the base of the carpet surface. And it's supposed to act similar to a natural grass root zone to support the underlying ligament. So we wanted to see whether that aspect altered the traction of these surfaces. So for this study, it was purely mechanical. We just did mechanical, translational, and rotational traction testing. And we can see stitch count and gauge both had a similar effect on the traction of the surfaces. So we could get changes of up to about 22% in the translational traction by altering those two components. As well, in terms of the rotational traction for those two components, we could have changes between 9 to 10% in the rotational traction. The presence or the absence of the thatch layer had no effect on the translational or rotational traction. So fibers can also alter the traction of these surfaces. So in terms of systematically going through these components, shock pad altering the surface stiffness can alter athlete performance. Altering the infill can alter the traction as well as the athlete movement patterns. And altering the fibers of the surface can alter the traction of the surface as well. So similar to that footwear study, we wanted to now combine all these different components and create what we termed was the optimal surface. So we took the optimal shock pad condition, the optimal infill condition, and the optimal turf fiber, and created a surface out of those components, and we compared it to the conventional control surface. So for this, we had 12 American football players, and they performed on both the conventional control surface as well as the prototype surface, which had optimal infill, shock pad, as well as turf and fibers. And these athletes performed sprinting and cutting movements, and the main outcome of this study was looking at those resultant joint moments at the knee and ankle joint. So here's the main results of this study. So here we have the peak frontal plane ankle moments in the control in black and prototype in blue. And on the right, we have the peak transverse plane knee moments, again in the control in black and the prototype in blue. And for these two variables, we saw a significant reduction on that optimized prototype surface. So these results, while positive, were not as large as we were expecting. So we were expecting some much bigger differences. And so one explanation of that could be due to the fact that there may be some interaction between these different components. So having the optimal infill, as well as the optimal fiber orientation, they may have counteracted each other and not really attributed the way we thought they would. Another aspect that we had is we had American football players, and this was actually from a separate study, but the results are still the same, or very similar, I should say. So when we collected data on American football, and we had skill, which would be speed players, which would be running backs or wide receivers. As well, we had power players, which would be O and D linemen. And when we subjectively assessed their preferences in terms of the surface, for the control, the power players, so the O and D linemen, actually preferred the control compared to the skill players. And more particular, when looking at the prototype surface, those power players actually had a negative subjective assessment of that surface. So they really didn't like that optimized surface. So one reason for this could be the fact that the height and mass of these athletes is quite substantially different. So the power players are taller as well as much heavier. And we also did some 3D body scans for these players. And here is just the image of one of our larger power players compared to one of our smaller skill players. So these players are substantially different in size, in speed. So it makes sense that these players who are quite different would potentially require different optimal sport surfaces or sport properties. So summarizing in terms of the sport surface, optimizing the surface can reduce these joint moments. Further investigation is needed into the different surface components and how they potentially interact with each other. And different preferences are present for different groups of athletes. So perhaps different groups of athletes may require different mechanical properties of the surface. So in terms of some future work on sport surface that we're currently doing, so one is looking into new infill materials. So the European Union recently passed a ban on microplastics. So this includes artificial turf, the rubber crumb. So I believe this comes into effect in 2028. So all the artificial turf companies are now looking at a surrogate to those rubber infill and specifically looking at different types of organic infills and how they can find the best organic infill for these surfaces in Europe. As well, some work we're doing is look to optimize the surface based on the users of that surface. So we showed in our shock pad study that performance can be altered based on the movement. So when designing a surface, you should really take into consideration the sport being played. So what is the main sport that's going to be played on that surface? And you should design for that specific sport. As well, looking at how the optimal surface properties may differ based on the participants. So preparing the optimal surface for an adult male or an adult female, as well as looking at the optimal properties for youth. So if the field is going to be mostly used by youth athletes, then they likely require substantially different mechanical properties than a surface that's optimized for an adult male. So overall summary in terms of shoe traction research, what we showed is that high rotational traction can lead to increased joint loads and joint moments. As well, that high rotational traction can lead to an increased injury risk. The goal when designing footwear and sport surfaces, at least for traction, is to maintain translational traction, which will help athletes maintain optimal performance. As well, we want to reduce rotational traction to potentially reduce that injury risk. We can use all this background data as we develop our footwear and sport surface innovations. So in terms of acknowledgements, as we finish up here, so our lab group members, so Mike, Robin, Brina, Jake, David, and Darren, as well the various sponsors and funders we have for these projects, Field Turf, Under Armour, MyTax, NSERC, and World Rugby. So thank you very much.
Great, thanks for the talk, Bill. Do we have any questions to get started?
Good, Bill. I had questions about the one paper that, I remember what the first topic was, there was Darren was on it, and it was looking at performance, and it seemed like performance kind of plateaued out. But I noticed like the speeds were like 3.5 meters per second, if I'm correct.
Right.
Have you ever pushed that higher to see if like there's any other inflection points as athletes get up to like fast speeds?
Right. So those athletes were running around a circle and it was a very tight circle. So that was the maximum speed that they could physically achieve in terms of running around the circle. So kind of the limitation is we need to do that for a bunch of different movements to kind of parse that out. And that would take a lot of time and effort. So I think we could get that curve for a bunch of different movements.
Right.
It would just take doing it. And in terms of a double inflection point, I don't think there would be. There might be different inflection points for different caliber of athletes, perhaps.
That's what I was wondering.
But I don't think there would be like a double one where, I don't see how there would be a double inflection point where they maintain their surface or maintain the performance and all of a sudden they increase it unless you add an intervention to help them break that hump or something.
Just a speculation question. So like, if you just sitting here where you are now with what you've done, where would you place this as a risk factor for non-contact ACL injuries in, let's say, the NFL?
Where I place what?
Place your findings, your results, like what you're seeing with those reductions in knee loading?
Yep.
How do you think that how much do you think that would contribute to reducing the risk? This speculation wise, how much do you think that would?
I think, I don't know how much, I think it's better. So if you can have a shoe that you can still perform maximally, but limits your loads and your risk, then I think that's beneficial. I don't know why you wouldn't want to do that. And I know, so we've worked a little bit with some of the groups that do the research for the NFL, and they do quite extensive testing of all the footwear that's approved for use. And so they actually provide a lot of that mechanical data to the trainers and to the team so they can make a little bit more educated decisions. So.
If I could speak to that circle running issue. Circle running produces centripetal force. And in order to counter that, you lean into the circle as you go around. That adds to the gravitational force that you're resisting. So the faster you go on a circle, it's more like running in greater gravity. So regardless of the traction, I think the performance of the individual decreases the faster they go. In other words, I don't think Young's study showed that there was no relationship between traction and performance.
Oh, yeah. Good point.
Can I comment on that? I don't know, if I was thinking about that as well, but I was thinking more of it from the fact that it's censored data. So you can't say that there's a ceiling to performance. So what I mean by that is like, there's only so fast you can run in a tight circle. And then, so maybe by the time they get to the high traction,
Yeah,
that's kind of peaked because of centripetal forces and things. Is that the same thing you're saying?
That's what I'm saying. So the expectation of the athlete is
Yeah.
not linear
yeah.
with speed.
So he did do some follow-up studies on that, looking at, if it was due to the joint moment contribution. I can't remember the exact results of all that other. studies.
Young Hee Chang and Roger Crom
Oh, yeah.
did the same study, but they tethered the individual.
Yeah.
So they ran around an anchored pole, so the centripetal force, they didn't have to resist it themselves, and they could run as fast in a circle as they could in a straight line.
Andrew, you have a question?
So for your translational, resistance and that you did you try loading it at like your performance guys and power guys level, or did you just always load those turfs with your cleats to like one given load level, or would that fall
Yeah, so
within your athlete?
yeah, so we try to, we do it at one normal load and try to use a representative normal load. For studies like that, where it ranges quite a bit, it's a little bit more difficult. So, but we do select a normal load in order to test it on, so that is a limitation.
You've ever thought of testing it at kind of a normal load for your performance players and then a normal load?
So we,
for your
yeah,
power players?
so we have done extensive testing in terms of traction, at different normal loads. And the relationship is fairly linear. And so if we have a high traction shoe at a low normal load, and a low traction, as we increase the normal load, they still, in general, will stay, the relationship between them will stay. So the high traction shoe will still have higher traction relative to the low traction shoe.
Maybe those athletes do the testing on the different surfaces in their preferred shoe, or was it a shoe you gave them?
It was the shoe we gave them, yeah. So the shoe was controlled for all athletes, they different sizes, but yeah.
Benno?
Very nice presentation, thank you. The injury may be the reason of the traction between surface A and surface B. But it could also be due to the fact that the properties are not the same for surface A. Let's say you have a hole or you have
Yeah,
and don't you think that the probability that injuries occur because of that are much bigger than the ones that an ideal surface with another ideal surface? I'd say,
yeah, I would say the injury data, so injuries are multifaceted. So there's a lot of factors that go into that. And like uniformity of the surface, I think is one big one in terms of, if you have an area of the field that's been used a lot, it probably has different properties than an area of the field that hasn't been used a lot. And that's also something that we're starting to look at to see, if that plays a role. But I think in general, what we showed with our data is there is at least some aspect of injury that seems to be associated with traction. So it does seem to play a part. Whether it's the prime driver, there's another part as well. That's something that we don't really.
but the differences were rather smaller than what we expected.
Yes, yeah, for sure. So when we're talking about infill and all that, yeah, for sure. So those have a minor difference. Rotational traction was reduced a fairly small amount. And that's why we followed that study up with a biomechanical study, because we wanted to see if those changes were substantial enough to change the biomechanics of the athlete. And in fact, for that study, they were, because the athletes did change their movement patterns, although they were relatively small, as you're saying, the magnitudes were low.
Yeah.
For the studies where you found in the footwear part of your research, where you reduced the rotational traction
Yeah.
and found decreases in the ankle and knee moments, were those magnitudes of reductions around the magnitude where you see relations with injury risk, or where would you place that? Like, did you decrease it enough where you could see reductions in injuries?
Yeah, I don't know how to answer. I don't think we'll ever know that, because injury studies are very time consuming and costly and hard to do. So to actually validate some of this stuff with injury data, and as Ben was saying, it's quite multifaceted. I think it's very hard to do. But I think there's enough kind of evidence that it shows that if you can reduce the rotational traction while maintaining that translational traction, there's really no harm to doing that. And it seems to push them in the direction to have a lower injury risk.
And just to follow up, for the turf ones where you found some reductions, but they weren't large, was the footwear that was used on the surfaces controlled, or did people use whatever?
Yeah, the shoe was controlled. So we tested the traction with a specific shoe, and then we had a full size run of that shoe that we offered to the people when they actually performed biomechanics.
So do you think there could be an optimal like combination of the footwear with the traction and then the surface where you could then use that combination to reduce it even further?
Yeah, and that's where it starts to get really complex, because traction is both a component of the shoe and the surface, and both of them together. And so, yeah, there could be specific surfaces in which you want a specific shoe. And so it gets complex in terms of mixing and matching those two components and trying to find the optimal combination.
I think I may have missed it, but for these injuries, like what was the kind of the inclusion criteria to count it towards these ones? Like what was the most common one? How rate was just every non-contact one was kind of attributed to this? Or-
Yeah, so for the injury study, we looked at non-contact lower extremity injuries in American football games. And they had to have missed some time from their practice or game, and they had to go see the athletic therapist, or else they have no idea of knowing the person injured. And then the most common injuries were to the ankle joint. That was the most common site of injury. Then, yeah, I don't know what other.
Yeah, so regarding your presentation on the injuries, like you said, the rotational traction and there's too much of it, it causes it, like there's a higher incidence of injury. I'm wondering how much of that has, like for the background of for athletes that you tested here, how many have gone through like neuromuscular training, because for like something like neuromuscular training could have an effect on if the athletes know how to land or they know how to where their foot placement and all that. Like how much of the injuries are actually the result of that rather than the footwear itself?
Yeah, so we didn't have extensive background information. So they did like a questionnaire before the study, giving us some base information. We didn't have any information on neuromuscular training they would have done before. I would expect or suspect that that was very low for this population group. But I don't know that.
Thank you. When you run and you want to change shoes, they usually like suggest you not change drastically. Your shoes get like the same side height or stiffness. If you want to change cleats, would you suggest you keep the same brand or similar shoe, or if you change drastically your cleats, can you increase or decrease the risk of injury?
I don't know, that's a good question. I would probably say it might be along the similar lines of those other components. That if you have if you're used to a very low traction shoe and then you go to a very high traction shoe, I suspect that might not be great. And you might want to try smaller increases. The difficult thing is there's no real way of knowing. So you can look at the cleats and try to see, but it's hard to determine how much traction some shoes have, especially now with they have these molded elements in the shoe, it's hard to look and determine, so that's a good point.
Something I think you alluded to with some of your graphs and talked about future work is that like between female athletes, adult athletes, and youth athletes, there could be differences in like body type and weight. And so I'm curious how and then with your power and skill player comparisons to the football player, how do companies sort of design around potential sort of weight differences in players? Do you think that plays a role in your traction calculation?
Yeah, so I don't know exactly how companies design based on weight. I would speculate that they would conventionally use just a typical adult male, and that's kind of the inputs they use to designing their surface. I think that what's coming out now is that we should probably consider how that affects different masses of people and different sizes of people, so youth and females. I think that's a very important thing that's probably been quite overlooked and not really thought about. And I think moving forward, more of these companies are starting to at least address that, or at least investigate that to see if that makes a difference. And if it does, then potentially do something to design to the main user group of the field, for example.
Me?
Oh, Venus, sorry.
Oh,
You can go next, Fran.
everyone is like, right?
Next, Fran.
So, I go, okay. In your study, when you wanted to find the best performance and the best, like the maximal, best performance and combine it with low injury, you tested rugby athletes, you
Yes.
said? And then at some point you said that these are the tractions that they were using / that they were required,
Yes.
and you compared everything to this, to these values.
Yes.
But how confident are you that these are good values, that they're not gonna lead to some injury later in these athletes? So how do you know these are like good values?
Yeah, so those are the values of the sample that we use. Is that, could we extrapolate that to the entire population? I think that would need further research to do. And I would suspect in terms of, so we developed kind of a cleat design. I would suspect before we would create that and like sell that you'd want to do much more extensive tests to ensure exactly what you're saying, that it actually works well for a lot of people, and it's not putting certain pockets of people at a greater risk than what they would be at with a normal cleat.
Fran.
Thank you. You focus primarily on rotational traction.
Yep.
And then Aaron Rodgers had this injury last year, and he would probably say it was because of translational traction. So I guess, put you on the spot here. So does the translational traction of the surface have anything to do with Achilles tendon rupture injuries in football?
So it could. The main thing that, so I looked at non-contact short-term injuries. Aaron Rodgers' injury was not a non-contact. So he dropped back to pass, and there was a lineman on his back and basically caused his foot to get stuck in the surface.
Yeah.
So it's a different mechanism of injury. There is a decent, so in our injury study, we also did look at the correlations between translational traction and injury. And it wasn't, I wouldn't say there was nothing there, but it wasn't as defined as rotational. So it wasn't as straight a line. So there could be something there, but it's not as apparent, and it doesn't seem to be as critical as rotation.
And in your expert opinion, if he was playing on grass, would it have been any different?
No.
Okay. Whatever happened to the swivel shoe? Okay, but
It was
it had these little, it reduced rotational, traction, right? It kind of rotated.
so it was locked.
Oh, yeah, and then it would open
And then it
up.
was completely open, so it was basically like on or off at a certain threshold, it was completely free to rotate. So I could see a lot of issue with that.
Yeah, so then you, yeah, so then you also made your own little, low low rotational traction shoe, and it was, you know, you grouped the studs all close together in a circle,
Yes,
and it was better. And so, but you never see a cleat that looks like that. So, I guess my question is do you have an example where, like, any of these interesting or novel cleat designs and things like that have gone to market? Have been put in place put into a shoe?
do I have an example of like stuff that we've worked on or?
Well, I figure, who else works on this?
So we worked with companies and we have seen, yeah, our concepts do make its way into footwear. I wouldn't say 100% of what we propose or there's different factors that come into play, but yeah, I would say that some of it has for sure.
What was the idea behind the blade sort of stud?
Fin.
What's it called?
Fin?
Fin, sure, fin.
So it was the blade shoes in general, they had the larger blades around the perimeter of the shoe sole. And so that would increase the rotational traction of that shoe. So I don't think, maybe the shape, the blade did come into play, but I think it's more the orientation of how it was around the perimeter of the shoe sole. The main reason as to why those shoes were associated or thought to be most dangerous. They likely increase that rotational traction because of that.
Also, there's a link with injury with wearing this.
I don't know what you mean by blade shoes.
Well, I mean, the soccer cleat design, that's not circular stud. That's kind of like,
Yeah, those I would term molded. So
okay,
they're not the cleats that you screw in, they're more molded.
yeah, but there's molded circular stud.
Okay.
Soccer cleats.
Yeah. I'm not really sure what you're asking.
Does anybody know the name of the shoes I'm talking about?
Well, baseball shoes are like that.
No, no,
They've got.
no, sorry, there's soccer cleats that do not have circular stud.
Yeah, they're like
I'm not
six
crazy.
sides. Yeah, edge or something like that, yeah.
I'm fairly certain they're called,
And you had
Bladed
made some for
spikes.
experiment to test the difference between rotational and translational. You had the cleats that were wider.
Yeah, right, yeah, exactly. So if those are what you're terming as blades, yes. So it all comes down to why when you put your cleat pattern on there, it all comes down to how you orient it, where you place it in order, and how that affects the rotational and translational traction. So to say just blades are more dangerous or increase risk, I don't think you can say that. It's how they're oriented on the
Okay.
sole.
and very quick question. Very quick question. Why does every single Calgary football high school play at Shoaldice? And how is it even possible? Are there 2 high school teams
No,
that only play on Friday night?
there's 3 fields and they play on different nights of the week. At different times.
Oh,
Brandon, you have a question?
I seem to remember a study in Scandinavia where they looked at injuries in soccer. And they did a study where they looked at the summer and then the winter. And the summer was played on grass and the winter was played on artificial turf. And surprisingly, they had the biggest number of injuries when they changed from one surface to the other one. And they were suggesting that depends because the friction properties are different. And then they did the study again from winter to summer. And what did they have? The most injuries when they changed. When they changed from the higher to the lower friction, so just the opposite then. Which suggests to me that the friction is not a good measure to
yeah,
look at the injury question.
I would probably disagree with that. I think that's an interesting study. I'm not familiar with it, so I'll check it out, but, Yeah, I think that goes back to Robin's point, the fact doing a quick change is probably not necessarily good. But if they saw injuries as well going from high to low, yeah, that's definitely interesting. There's other properties of the surface that change, probably the stiffness, probably most substantially would change between an artificial and a natural grass.
Everybody was from summer to winter to summer,
Yeah,
and
no, that's a,
the change was in one direction and then in the other
Yeah.
direction.
no, I'd be interested in seeing that study, so.
I was wondering if there's room for regulatory change, as opposed to being concerned about performance, because equipment is generally regulated like crazy and what's allowable. And equipment rules change based on all sorts of things, including safety, and often at a small cost in performance. And so I feel like, just pure performance is sort of an interesting thing, but I don't think it matters that much in most competitions. So like, if everyone's using the same, subject to the same limits on their cleats, then maybe for the viewers, it still looks like a football game. And we can still enjoy it. And so how about regulations?
No, that's a good point, and I think that's something, at least in our experience, my experience working with some of these companies, they, yeah, I think regulation is tough, but I see where you're getting at. If you change the surface, for example, and make it, maybe it reduces performance 25%, but it's much safer. Everyone's performance reduces 25%, and so the performance isn't as big a deal. So, yeah, I see what you're getting at. I think, yeah, no, that's a good point.
Well, I think this even existed decades ago, because when I played age 12 soccer, I remember we were not allowed to have screw-in cleats. And so I'm presuming that there was already an idea of back then of this trade-off.
I have a quick question.
Yep.
So I'm not really familiar with the shoe space, but like thinking to is there a standard for measuring the traction of these shoes? And I'm thinking more towards the like friction and typology work in slips, trips and falls. But they have clear ISO standards that they have to follow when they test in dry and wet conditions. So is there any like standard like that in the sport traction space?
There is for surfaces. And so it has to be more with FIFA. So they have FIFA quality standards. And for that, they have conventional tests where they have to go to the field. And that's where they can certify whether they're FIFA Pro or something. And then FIFA. So there are some standards, but I wouldn't say it's not widespread. And specifically for footwear, I would say yeah, there's not any standards for shoes.
Oh, any question?
My question is about the movement patterns. So you compare your shoe, your design of the shoe with another one, and the test was the athlete runs forward and makes a sharp turn, right?
Yeah.
And the most traction is needed with the athletes that doesn't turn, right?
Yeah.
Did you compare the motion of the other instances that doesn't require the great traction, such as you don't have force place, but did you look at the center of mass movement or velocity? Because I'm thinking, if I'm running and I know I will not have much traction when I do the sharp turn, and if I need to complete a test in a given time and distance, what I would do is I would run faster when I need less traction. I would slow down when I need the traction most because I don't trust my shoes. And then I will run faster again after I complete the turn. That means the instances that doesn't require high traction, the center of mass or all that is doing something different. Have you compared the strategies between this?
We did look at, so I just presented the main differences. We did a bunch of different movements. So we did some straight runs as well as some other type of runs. And we looked at other movement patterns. We didn't have full body marker set, we just had lower extremity. So it makes center mass a little bit more difficult. We did have pelvis markers, but I'm not sure if we looked specifically at the center of mass movement for those. But the athletes, when you change the traction, they change their moments, but they also do alter their movement patterns slightly.
Okay, mine.
Yeah.
Second question, very related. So the optimal shoe reduce the moments, right? Angular
Yes.
moments, okay. Then where did the moments go? And then I want to answer that. If I slow myself down, and if I don't have much traction, let's say I'm running, I'm gonna do a sharp turn and there's some piece of ice, but I'm gonna step on the ice, but I still need to do the turn. I would like to work with my muscles, very negative work, and generate all the moments and slow myself down, then make the turn and run. But if there's some traction, I will do it more passively. You know, I will hit the ground as long as it doesn't hurt. Then I would rely on passive dissipation. Has anyone ever looked at this? What do center of mass do with these instances? Rather than just looking at only the angle.
I don't think so. I don't think anyone's done it. It would be something interesting to look into. And perhaps we could look through some of our old data, because we do have markers of the hips, so we could look, use the pelvis as surrogate of the center mass.
But do you agree with what I'm saying? Generally, the strategy is like passive dissipation because of due to high traction. Should satisfy. Does that make sense?
A little bit, you'll have to explain it more to me.
Matt?
I was gonna wonder, when I was looking at your bar plots, how consistent were the individual participants? Did they all tend to show the same trend, or did you have some individuals that were?
Yeah, so we had a statistical difference, so that shows the majority did go in the same direction. I wouldn't say they all did, and we might have some outliers that did go the opposite way. Off the top of my head, I can't remember how many, but the percentage is probably low.
And there's no way to, like, I guess where my head keeps going, maybe it was because you led with that, one slide where you put up the lineman versus the skill players, and you sort of said, hey, there seems to be something in there that might change based on the body size. And so do you think, like, how do you think your results would hold up if you were to say, look at, you know, I don't know, the skill players and the linemen and sort of go to different body shapes? Do you think you'd be able to have, do you think you'd have similar findings? Would it be similar, similar between the groups? And
Yeah, so that's where, we didn't have a big enough sample size to do that in here, but that's what we started to do, and we did start to see some trends. So we did some follow-up studies where we did, 4 surfaces, I believe, and linemen and skill players that I didn't present. And again, we didn't have a big sample size to compare between those groups, but we did start to see differences in, 1, the preferences, but 2, the movement pattern. So certain groups of athletes, they behave differently on different surfaces for the same movements. So it seems to be that, the properties of the person, the size of the person, they kind of like and prefer, both in terms of their biomechanics as well as their overall preference, specific properties, and those properties can differ based on the person or the size of the person.